All right, let's dig into something you deal with every single day, but maybe never really stop to think about: series versus parallel circuits. We're going to find out exactly why plugging in your toaster doesn't make all the lights in your kitchen go dark. I mean, really think about it. You've got the fridge running, maybe the microwave is going, the lights are on, but when you unplug the toaster, the fridge doesn't just stop. Why not? Well, it all comes down to how things are wired up. So, to really get why your kitchen works the way it does, let's first imagine a kitchen that's wired up in, well, pretty much the worst way possible. We'll call this the all or nothing circuit. Just picture it. The electricity has to flow from the wall, through the lights, then through the microwave, and then through the refrigerator, all in one long single file line. Every bit of that current has to pass through every single appliance to get back home. Okay, so what if you just unplug that microwave? You've basically just created a big gap in that single file line, right? The path isn't complete anymore. So, what does that mean for everything else in the chain? Yep, total blackout. The whole circuit is broken. Because there's only one single path for the electricity to follow, a break anywhere just kills the whole thing. It is literally an all or nothing situation, and, a really terrible way to set up a kitchen. So this kitchen catastrophe we just imagined, it actually has a technical name. It's called a series circuit, and its number one feature is that single path. The main thing you've got to remember here is that everything is connected end to end. That's what creates that one and only one path for the electricity. No detours, no side roads, nothing. Okay, let's break down these traits. The first two, we pretty much get those already from our kitchen nightmare, right? Single path, one breaks, and they all fail. But check out this third point. If you've ever seen old cheap holiday lights, you know this one. The more bulbs you add, the dimmer they all get. That's because they all have to share the total voltage. And finally, resistance, that's how much the circuit fights the flow of electricity, is super simple. You just add up the resistance of every single thing in the line. So if series circuits are so bad for wiring a house, there's got to be a better way. And there absolutely is. So let's meet the hero of our story, the parallel circuit. So instead of one long chain, think of it more like a highway with a bunch of off-ramps. Each one of your appliances gets its very own off-ramp, or its own branch. The electricity gets to the highway and then can choose which path to take. And this structure, it changes everything. The current splits up, so if one branch closes, like you unplug the toaster, the other branches going to the fridge and the lights don't care, they just keep on working. Plus, each branch gets the full voltage from the source, so nothing gets dimmer. But here's the really weird part. The more branches you add, the lower the total resistance gets. It's like opening more checkout lanes at a store. More paths mean less traffic, and the flow is just easier. All right, so the concepts make sense, but the numbers? The numbers are what really make it all click. Let's see just how different these two circuits really are when we boil it down. This table is the perfect cheat sheet. In a series circuit, the voltage gets shared, which is why things get dimmer, but in parallel, everything gets the full voltage. For current, in series, it's the same everywhere. In parallel, it splits up. And then there's the big one, resistance. In series, it just keeps adding up, choking the flow. In parallel, adding more paths actually makes it easier for the current to flow. So let's throw some actual numbers at this. Let's say our 3 kitchen appliances in that broken series circuit had resistances of 8 ohms, 8 ohms, and 2 ohms. To find the total resistance, you literally just add them up. It's that simple. Add them up, and you get 18 ohms. Remember that number. It's pretty high because the current has to push its way through every single one of those components, one after the other. Now for parallel circuits, the math looks a little funkier, I'll admit, but don't worry, it perfectly explains why they work so well. It's just a simple 3-step process, and it shows how adding more lanes to our highway makes traffic flow better. So we take those exact same resistors, the 8, and the 2 ohm ones, but now they're on their own branches. We set it up by taking the reciprocal of each one, so we get 1/8 plus 1/8 plus 1/2. We add that up and then flip the final answer upside down, and what do we get? Just 2 ohms. Seriously. 2. Think about that for a second. We went from 18 ohms all the way down to 2, using the exact same appliances. That is a huge difference. And this chart just slams that point home. It's not even close. So here's the key takeaway. With so much less resistance, a parallel circuit lets a much bigger total current flow from the wall. And that's exactly what you need to power a bunch of hungry appliances at the same time.
And that brings us right back to the beginning. We've gone through the theory, we've looked at the numbers, so let's tie it all together and answer our original question for good.
This is it. This is the answer. The entire electrical system in your house, in my house, it's all one giant, complex, beautiful parallel circuit. Every single plug in your wall, every light switch, it's its own independent branch that connects back to the main power line. And that is why you can have the TV on without needing to run the dishwasher. Each one works on its own because each one has its own path for electricity. So next time you pop some toast in the toaster and the lights don't even flicker, you'll know exactly why. You can thank the parallel circuits in your walls. But that leaves us with one last little puzzle. Knowing how bad they are for houses, can you think of any time when an all-or-nothing series circuit is actually the better choice? Here's a little hint. Think about things that are designed for safety.